Okay, well, welcome. Here is a little video lecture on how to solve limits analytically. And I'm going to split this up into identifying how to review the definition of a limit, when limits don't exist, continuity, and how to solve limits analytically, specifically with direct substitution, dividing out, rationalizing, and then I'm going to have another video on using properties of limits and transcendental. So, without further ado, let's do this. All right, so we talked about how to find limits. And limits is an informal definition, and this is a bunch of stuff I had in previous videos and previous lessons, is that what you basically want to see, a limit is a y value that becomes arbitrarily close to a unique number L. Okay, and how do you do that? Well, you have to approach x or c from either side. So as you start inputting values of x close to c, all right, and as these outputs, they will get arbitrarily close to a unique number L. And if they approach the same number from both sides, we say that the limit is that x approaches c of f of x equals L. And this is what we have. So from the right side, we have a little plus sign. So as we approach c from the right, all right, we get a value. And as we approach to the left, we get a value. And if both those values are equal, they will equal L. They will equal L. So to show you how to do this algebraically, we know that solving limits algebraically, you have to identify first what is the continuity. All right, so what is the continuity when you're talking about these different things? So I'm going to get my highlighter. Key thing is if it's continuous at C. Now, if it's continuous at C, we know a lot of different things. If it's continuous at C, that means that the value of the function, that's why f of c, is going to equal f of x, whatever that function may be, rational and whatnot, all right, polynomial, whatever it may be. So if it is continuous, then if you substitute the value in for the function, then it will actually equal the value of the function if it is continuous at C. So that's the first thing we do. If it is not continuous, all right, if it is discontinuous at C, so you get a value that gets you 0 over 0. Okay, 0 over 0. And I probably should put f of x over g of x, but if you have this and you plug it in and you get 0 over 0, all right, talking about a rational function, all right, then what we know it is discontinuous at C, and we actually are kind of thinking there's removal of discontinuity at C. All right, removal of discontinuity means there is just one value that's being removed from the graph. And so how do we do that? Well, you see if there's direct substitution, intermediate, if there's indeterminate form. Indeterminate form means you cannot determine what the limit is, simply by plugging values in. So there are other things that we need to figure out in order to solve that, okay? So we need to simplify into an equivalent and continuous function at C, so direct substitution can be applied. So in other terms, last thing is if there is any other discontinuity, then the limit doesn't exist because it will approach different values from the right and left side. So let's try out some problems of how to solve limits algebraically, shall we? Yeah, let's do this. All right, so continuous function at C. So if I was given this function right here, and I were to plug in a value there, we would figure this out and what this would look like. So I would just simply, all right, want to figure out if that is going to be continuous. All right, so I would take 3 and I would plug it in there. I would do 3 squared, all right, minus 3 times 3, all right, minus 10, and that would be 3 minus 5. Okay, 3 minus 5. Well, when we have that, we have 9, all right, minus 9, minus 10, all over, that's going to be negative 2. Simplifying that, all right, these will cancel out, and then we'll have negative 10 over negative 2. All right, well, that's cool, which equals 5. All right, well, it appears that we receive a value, so I'm assuming this is continuous. Now, to verify this, I'm just going to go on Desmos, and I'm going to graph this. And you can see that I already graphed this function right here. I put this in Desmos. And if I go on my value and I kind of start approaching, all right, 3. So as I get closer and closer and closer, this is from the left side. So I get closer to 3 from the left. You can see that it appears we're getting closer and closer to, all right, yeah, it's getting closer and closer to 5. And from the right side, it's the same thing. If I go to, all right, a table, I can plug in some values here. So if I want to go closer to 3, the left would be like 0.9, and then I can go 0.99, all right, 0.999, and all these different values. You can start seeing that, yeah, 4.999, that's getting really close to 5, all right. And if I plug in 3 itself, I can see it's 5. If I go to the right side, like I'm plugging in 3.1, and then 3. Probably should go, all right, 3.0, 0, 0, 1. All right, there we go. And if I want to go in descending order, 0, 1. All right, 3.1. Now, do you have to do that for all the different values? No, you don't have to do that for all the different values. All right, but we can kind of verify, or we can verify using a table of values that yes, we can see that as we push from the left side and from the right side, it appears they both are approaching the value. And we confirm that it's continuous by noticing that the value at 3, all right, of the function is the same as both of the limits from the right and left side. And therefore, it's continuous. And by using direct substitution, this is what we're doing, direct substitution, called it direct sub, we can verify that just by plugging the values into the function itself. Now, this is when you have something that is continuous at C. Now, the thing is that that's not really cool, and we use limits a lot for this reason, all right, to define continuity. However, the big deal is we want to determine what happens at values when they're discontinuous, all right, discontinuity. So the same function, but what happens when I plug in 5 into this one? So if I plug in 5 into here, all right, I get 25, could be 5 squared, minus 15, all right, I'm plugging 5 into there, minus 10, all right, all over 5 minus 5, and what we have that is 0, so I have 0 over 0. This is what we call indeterminate, all right, indeterminate form. Indeterminate form simply means that we cannot determine the value of the limit by plugging values in. It's indeterminate form. It also tells us that our value at C, all right, value at C, in this case C equaling 5, is undefined. All right, is undefined. Now, 0, 0 also tells us what type of discontinuity this is. 0, 0 usually means, all right, we have what's known as removal discontinuity. If we look at our graph, I'm going to go back to Desmos here. I look at my graph right here, and I'm going to plug in some different values. So instead of being at 3, all right, let's take this and let's plug in 5, value close to 5. Well, I plug in a value of 5. I can identify that it's undefined. Let's go to the right of this. So, to the left of this, that would be like 4.999. All right, right here. If I take this, and I'm just going to put in a 4 there, and I go over here and plug a 4 here, well, it appears that this value, if you can look at it, is of going to 7. All right, it appears the intended height, the value of the function to the left is going to 7. Let's just verify this over here. If I plug in a 5 there, oh yeah, definitely 7. All right, plug in here, you can see that, yes, it's getting closer and closer and closer to 7. And if you do it graphically, all right, I can identify these values, and we can see that, yeah, as we get closer and closer, look at the x value, as I get closer and closer to 5, it appears that this value is going to 7. All right, and so our limit appears to be 7. Now that's awesome, and we can do that graphically, all right, and using a table. However, how do you do this algebraically? Well, this is where we're going to use some algebraic techniques. Now, for the rest of this video, I'm not going to go to Desmos anymore, because when we get 0 over 0, we know this is indeterminate form, and we're going to have to simplify this. Now, when you have a polynomial like this, we're going to simplify this by using what's known as dividing out, all right, the dividing out technique. All right, so this is how we're going to simplify. So whenever you get 0 over 0, the first step is step 1, simplify. Our goal, eliminate the denominator. I will eliminate the denominator. All right, well, in any case, what we're going to do is we're going to take and we're going to divide this. So we have to factor this. I'll give you a little hint. One of the factors will be the denominator. So in the top, we're going to have x minus 5. If I just pick that one, well, what other value will I have? Well, that's going to be x plus 2. All right. Yeah, because negative 5 times 2 is negative 10. All right. Negative 5 plus 2 negative 3. There you go. And when we have this, we have x minus 5. And boop, boop. All right. What will happen is that with this canceled out, and what we have now is a new function, all right, a simplified function, which is actually the same as this function everywhere. So if I'm going to go to this one more time. If I actually graph this function right here, I put in y, all right, equals, what was, oh, all right, what was it again? All right, x plus 2. So y equals x plus 2. You see that that actually overlaps this function exactly, except for this one. it's actually defined at 5. So if I actually go to 5, all right, plug it in there, you can see that it's actually going to equal 7. Yeah, it's actually 7. And so this function, we eliminated the whole, all right, eliminated or removed this continuity, and we can now use this continuous function, which is equivalent to this one everywhere except for x at 5, and we can now take this limit. And so we're going to take the limit, that's step number 2. The limit, all right, as x approaches 5, for this function right here, x plus 2, all right, that's going to be, all right, equal to 7. By using their substitution, just plug it in there. 5 plus 2 is 7, and there we have it. That's our limit. That equals L. All right, that's it. So once you figure that, divide out, cancel something out. Step number 2 is you use direct substitution. All right, you do it and you find your limit. All right, let's try some other problems. All right, here's another one. All right, so first thing to do, see if it's continuous at C. So how do you do that? All right, to find out if it's continuous, you always start with direct substitution first. So start always, all right, with DS, direct substitution. See if it's continuous. All right, all right, so plug in 2. 2 to the 5th power is going to be 32. Minus 32. That's a horrible right there, 2 minus 2. And well, guess what we get? We get 0 over 0. We got a whole here, all right, whole. So because this is a polynomial of a polynomial, we're going to use the dividing out technique, all right, because the next we have to do is once we get indeterminate form, all right, that's indeterminate form, all right, we know it's, all right, undefined at C, so we're going to still figure out what this limit is because we know it is removable discontinuity here. So this is removable discontinuity. This removal discontinuity is whenever the value of the function does not equal the limit. Okay, so you know whenever the limit exists, so as x approaches C for this function, all right, this equals L. However, this does not equal the value of the function. Either that's undefined, all right, but those aren't equal. The limit exists, but the value of the function is not equal to that. That's what we know as removal discontinuity. So we're going to use dividing out technique, and we're going to divide this out. Now, this is a little bit harder to factor. So we're actually going to divide x minus 2 into, all right, x to the 5th minus 32. So we're going to use long division here. So I'm going to practice doing long division. All right, so we have here, I'm going to go plus 0. I got some zeros in here. It's the 4th, the 3rd, quadratic, the linear, and then we have minus 32. All right, maybe some of you know synthetic division as well. That works as well. All right, so what do we have here? What times x, because it's x to the 5th? That's going to be x to the 4th. All right, multiply that through. We have x to the 5th minus 2x to the 4th. All right, bring through the negative. Right, long division, we have to bring through the negative. That canceled out. Bring that down. And so we have is 2x to the 4th. All right, next one, what times that? It's going to be plus 2x cubed. All right, multiply that through. Bring down to 0. Okay, whoop. All right, plus another 0. And so we have is 2x to the 4th. It's going to be minus 4x cubed. All right, change that to the opposite and opposite. All right, and what we have then right here, okay, going back, we have 4x cubed. All right, bring down to 0. Man, long and tedious, right? All right, plus 4x squared. All right, multiply that through. There is a faster way if you know how to factor difference of squares. There is a formula for doing this. Unfortunately, like most math students, and me being a math teacher, I always forget the formula because I don't use it very often. All right, plus right there. All right, cancels out. This turns into plus 8x squared. And then now we bring down to 32. And guess what? I'm writing on an angle, but that's okay. We have this plus 8x. Did I forget a 0? I think I missed a 0. It's going to work out. All right. What we have right here is going to be x squared. Oops, don't bring that down yet. It's going to be a 0. Sorry. All right. I don't even know that. Well, when we go right here, we're going to have 8x. We can kind of see 1, 2, 4, 8. All right. Next one's going to be probably 16. But just to go through, 8x squared. We have minus 16. All right. X And the last thing right here is negative plus positive, cancel 16x. Now we can bring down the negative 32. All right, that's going to be plus 16. And yes, it does cancel out. Negative 16 minus 32, negative positive, bring down negative 32. Cancel, cancel. No remainder. Remainder is equal to 0. And therefore, this is our new function, which we're going to figure out now by take the limit now as x approaches 2 of x to the 4th, all right, plus 2x cubed, all right, plus 4x squared, plus 8x, plus 16. You plug in the 2. 2 to the 4th is going to be 16. All right, this is going to be 16. This is, guess what? 16. This is 16. This is 16. And 1, 2, 3, 4, 5. 5 times 16 is going to give you 80. I believe it's 80. All right, and that is our limit. That's our limit, my friends. All right, and we box that in, and that's what we have for our value. All right, so that's dividing out technique. All right, another one. All right, a little bit harder. Let's say we have this. We have the limit as delta x approaches 0 of x plus delta x squared minus x squared over delta x. All right, now it's a little bit weird because we have two different variables. We have delta x and we have x, okay? And we're going to plug 0 in only for delta x, so don't be confused here. All right, so this is what happens in algebra sometimes. So what do we do with x? X is just coming along for the ride. So when we do that, we plug that in there, we're going to have x plus 0 minus x squared over 0. What will happen is, that's a square there. What will happen is that these x squareds will cancel out because we have, yes, x squared minus x squared over 0, and we have 0 over 0. Okay, well, 0 over 0, once again, is indeterminate form. Okay, there's some sort of removal of discontinuity. All right, indeterminate form right there. All right, so what we got to do is we're going to, once again, we have a polynomial here. We're going to not divide, well, we're going to divide out, but first, before we divide out, we're going to just factor. All right, we do some algebra. We're going to simplify. Remember, we're going to simplify. So here, we are going to divide out, but I'm going to start with factoring. We're going to use algebra. I would say we use algebra first. All right, so we're going to use algebra. We're going to FOIL this through. So we have x plus, all right, delta x times x plus delta x, all right, minus x squared all over delta x. When we have that, it's going to be x squared. Right here, we're going to have plus 2x delta x's. All right, do not multiply this through. There's two different variables. And then we have plus delta x squared, all right, minus x squared all over delta x. What you notice is that, yes, something will cancel out. This and this will cancel out. We're then left with 2x delta x plus delta x squared over delta x. Now, right here, we can then simplify this a little farther because one of these things is just like the other. What can we factor out? Yes, we can factor out a delta x. When we factor out that delta x, we have 2x left over plus delta x all over delta x. Cancels out. All right. The last thing is, what's our simplified function? Well, 2x plus delta x. Now, my friends, this is what we call the difference quotient. Someone took out the difference quotient, and we're using limits here. We're going to use it a lot when you get to differentiation and derivatives. So you might want to know that one. That's the one you might want to put in the back of your head. All right, and now we're going to take this as approaches 0. We plug in 0 only for delta x, and we get an answer of 2x right there. And that's our solution. That's our limit. Yeah, it's a variable. But that can happen. We're going to do that a lot more in the future. So a little bit harder. But dividing out and factoring. Algebra is king. As I would say, algebra is always king. All right, so using divided out technique. All right, and whatnot. So we're going to continue on. So if you want to pause and write this down, whatever, please do so. But now we're going to go to some other techniques. All right, one where you see some square roots. Okay, some square roots. So if I had this one, I have x over the square root of x plus 1 minus x. I would do the same thing. Always start with direct substitution. You want to figure out, is it continuous at C? Now, one thing you can just figure out, we have 0 up on top, so you always want to plug it in first. We have the square root of 1 minus 1, square root of 1 is 1, so we have 0 over 0, yes, indeterminate form. All right. Again. All right, indeterminate form again. So guess what? We have removal discontinuity. We got indeterminate form. And so now what we got to do is we have to simplify. Now, unlike all the other ones, all right, this is not a really nice, all right, equation to factor. So we're going to use is another technique, which is called, all right, I call it the conjugate technique, all right, or it's called the rationalization. That's what most calc books call it, all right. I also call it the conjugate. The reason why I call it the conjugate or rationalization is you want to eliminate the square root. Now, to eliminate the square root, what we're going to do is you always multiply by the conjugate expression of that square root, wherever it may be. So we want to eliminate this. And so what we're going to do is we're going to take that, the square root of x plus 1 minus 1, and we're going to multiply by its conjugate. The square root of x plus 1's conjugate is plus 1. These are conjugates of each other. There also can be the difference of squares. All right. So when we have this, we're going to have the square root of x plus 1 plus 1. And now we're going to do our algebra. This right here, I'm just going to take x times, don't distribute this through. All right. Everything is very, very nice. It works out smashingly when we do this. All right, but we take this times this, so we take our innings, we have to FOIL. So square root of x plus 1 times square root of x plus 1 is going to give us x plus 1. Our middle terms, because they are conjugates, will cancel out. All right, so these negative square root of x plus 1, maybe I'll just write it out for the first time, negative x plus 1, and then we have plus square root of x plus 1. This will always happen every single time, so I don't write this out ever, but I'm just going to do it just for the starting out. So you can see that, yes, these will cancel out. All right, I just FOILed. Just so you know what I'm doing. If you're familiar with that, I'm just FOILing that this times this and that. Now from here, we are now going to simplify, and I'm going to keep this on top. All right, and we have the square root of x plus 1. A lot of writing here. I know. All right, these cancel out, and now I'm left with x plus 1 minus 1. Well, guess what? This and this cancel as well, and then I'm just left with x. What? Look at this. This and this cancel. Awesome. So what do we have left over? Well, our equivalent expression to this one. Remember, that's what we're getting. This expression is now continuous at 0. It's the same graph as this one. We graph it on Desmos or wherever you graph a calculator, and you realize that this function, if you created a function and wrote it in, is the same as this function. Okay? And so when we take a limit now, as x approaches 0, we have filled in the removal discontinuity. The filled in the hole, all right? And now we're going to use direct substitution. Plug in 0, we have the square root of 1 plus 1, which equals 2. That's our limit. That's our answer. Using the rationalization technique. When you use this, the conjugate is whenever you see square roots, like this one. Try another one. Go green this time, all right? Plug the 2 in, always plug the values in. Doesn't have to be 0. Always plug the values in. Make sure you check to see if there is. So always start with direct substitution. Always start with direct substitution. Verify that this is not continuous at C, all right? That you have indeterminate form. So we have 4 minus the square root of 18 minus 2, which is 16. Square root of 16 is 4. Yeah, you can see that this is 0 over 0. All right, indeterminate form. Verify that. Awesome. Indeterminate form means there is a limit. The limit does exist. This is removal discontinuity. All right, the limit does exist. I repeat, the limit does exist. There are valuable or other functions. All right, when it's not indeterminate form, then we have a problem. Okay, and we'll talk about that later. But 0 over 0 is indeterminate form. There's a removal discontinuity here, and we're going to get rid of it. We notice what technique would we do algebraically to solve this? Well, we see a square root in the denominator. All right, none here. So we're going to take the conjugate of the numerator in this kind, whatever the square root is. So we're rationalizing. All right. Rationalization technique. All right, so let's rationalize this. That AKA is a conjugate. Conjugate. All right. so let's try this out. If we take this, we're going to have 4 minus the square root of 18 minus x, all right, over x minus 2. And group these together. I'm only using the conjugate of the square root. So I want to get rid of the square root, so I'm going to use the conjugate here. That's the thing that's bothering me. And this will cancel out. That's what's also going to happen. All right. All right. We have this. We only add when you do conjugates. It's only the value. All right. The sign that is between the two exponents. So we do not change any other signs. Sometimes students get confused with that. Conjugates. All right. When you have the difference of squares, we're basically creating the difference of squares. All right. That's why we're doing this. All right. Difference of squares is very, very powerful in mathematics, especially when you factor. Very nice. All right. So we're going to FOIL this now. So remember, we're going to FOIL this. Okay. So now we're going to FOIL. All right. What will happen is that since we do have the difference of squares, we have 16. The middle terms will cancel out. Then we're left with minus negative. So we're taking the square root of 18 minus x times the square root of 18 minus x, but we have the minus there, so it's going to be negative 18 minus x. All over, do not FOIL this through. No need, because x minus 2 will cancel out. If it doesn't, then we screwed up. All right. All right, algebra. I know this. And you will too. All right, I hope. No, you will. All right, so when we got this right here, make sure you distribute the negatives through here and here. All right, so we got to go and we have 16 minus 18 minus, so it's a plus x. All right, and right there we got x minus 2, and we have 4 plus the square root of 18 minus x. This top, hey, look what happens. The top will turn into x minus 2. All right, I rewrote it. I put the x in front, but 16 minus 18 is negative 2. And if you just so happen to realize that that also is what's in the bottom here, all right, so if I have this, all right, 4 plus the square root of 18 minus x, these will cancel out, these expressions, 2. And so now we've come to a simplified value that we can now take the limit of. We've now created and identified our equivalent function in every way, shape, and form except, all right, now defined at 2. All right, so we're taking the x as approaches 2 now. And we plug that in. 4 plus the square root of 18 minus x. And what do we have? 1 over 4 plus the square root of 18 minus 2. Well, that's going to be 16. We have 1 over 4 plus 4 then, all right, which is going to be 1/8. And guess what, my friends? That is the limit, all right, of this function. All right, 1/8. That is where that is approaching. And that's how you can solve it algebraically. All right, using good old conjugate. Oh, delta x, y. All right. So let's try this one. I have 2 more to do. I know this is getting a little long. If you want to fast forward any part of this, go right ahead. All right, but it's good. So if you want to try this one on your own and then look through the answer, that'd be swell. All right. Okay, so you'll pause it. All right, I'm going to go through the answer real quick. All right, we're going to have this right here. Once again, I plug in delta x equals 0, the square root of 3 minus the square root of 3 over 0, which is 0 over 0, indeterminate form. That means we got removal discontinuity. That means we have to do something. Well, we have the square roots here. All right, square roots. So square roots tell us we're going to use the conjugate. All right, rationalization techniques. So we're going to take this 3 plus delta x, all right, minus the square root of 3. And we're going to multiply this expression by its conjugate. All right, actually we're going to multiply this expression by 1 because that's why we have to use the conjugate, top and bottom. All right, because we have to multiply by 1. I didn't mention that before, but that is the reason why, because we can't. This is just a function, and we can't change the value of the function, so we have to multiply by 1. All right, and that's why we're doing the top and bottom. All right, that's why it's legal. Okay, just so we're not breaking any math laws. All right, we don't want any math police coming after us. All right, there's no such thing. All right, so once you have this, all right, what do we got here? Well, this and this will cancel out. We have 3 plus delta x. Right here, it's going to turn to -3. The middle terms cancel out. We're going to have delta x, and over right here, we have the square root of 3 plus delta x plus the square root of 3. Ooh. All right, right there. we can cancel out this and this. You then will see that this and this will cancel out, all right, after we cancel those out. And what we left with is equivalent expression to this function right here, 1 over the square root of 3 plus delta x. Oops, should have had this square root all the way over there. Apologize. All right, a little too big. I apologize for that. Hopefully you caught that. Okay, square root of 3 delta x. That's going to be plus the square root of 3. All right, and we're going to take the limit as delta x approaches 0. So yeah, that shouldn't be over there. Sorry. All right, but you plug in 0 in here, and we have 1 over 2 square roots of 3. That's our limit. We can simplify this. We don't like square roots in the bottom. We multiply top and bottom by square root of 3 over square root of 3. Or you could leave it. All right, but square root of 3 over square root of 3 times square root of 3 is 3. So that would be 6. So square root of 3 over 6, and that would be technically our proper limit. That's what we got. All right. One more final thing. All right. I'm doing this. Yeah, this is a long video. I can feel it myself. All right. But one other time you see, and this is our final rationalization. You don't see this very often. Usually dividing out and rationalization are the two main ones you see. However, sometimes you have a fraction over a fraction, or something that is equivalent to a fraction over a fraction like this. And when you plug the values in, all right, you try direct substitution first, and you realize you have 0 over 0 when you plug it in. All right, 1 minus 1 is 0 over 0. So how do you solve this one? Well, whenever you have this, you want to eliminate the denominator, okay? You want to get a common denominator, eliminate the denominator, whatever the case may be. Now, usually what I do right here is I get a common denominator, all right, and I simplify this using algebra. Yes, all this is using algebra, all right? Algebra is your friend. So right here, I'm going to take this, and this is what I would do, is that I want to eliminate this denominator, okay, right here, okay, because we don't want a fraction over fraction. So I'm going to multiply top and bottom by 1 by the common denominator of these two. And this, in this case, is just x plus 1. Top and bottom. When we do that, what happens is you distribute this to here, and you distribute it to there. And what you get then is this times this would turn out to be 1 because the denominators cancel out. This we have minus, because that times that is going to be minus x plus 1. And right here you have x times x plus 1. Do not cancel anything out. And so we're going to now simplify that. So that's all you have to do. We have 1 minus x minus 1 all over x. We have x plus 1. Once again, we're looking to cancel things out. This and this will cancel out. I'm just going to write this again. So now we have negative x over x plus 1. Make sure you distribute this negative through. A lot of people will forget that. A lot of students will forget that. That's not good. This and this will cancel out. We're left over with the negative 1 on the bottom. And so we have an equivalent expression of negative 1 over x plus 1. And so now this is defined at 0. All right, defined at 0 now. So now we can find the limit, because we've made it continuous at 0, as x approaches 0. And right here, I get negative 1 over 1, which gives me negative 1. That is our limit. That is where that is approaching. Cool beans, right? Cool beans. All right, so that is what we have there. Common denominator, and that's what we do. All right. So with that, really quick, final part of this lesson. All right. You can write this down if you want to do this. This is using the properties of limits. Just going to go through this real quick. All right. With the properties of limits, we take the limit as b and c. All right. If you have two limits right here, and you want to figure these out, what you have is you simply take the limit of 1, all right, is x approaches c of fx, if it's defined as L. And you take the limit of g of x approaches c is k. Essentially, you can use these 5 different properties. Scalar multiples, all right, means that if I just multiply b by some sort of function right here, it's going to be b times L, if we already know what this limit is. If we have two functions, like f of x and g of x, and they're being added or subtracted, and we take this limit, well, it's simply going to be the limit of f of x plus or minus the limit of g of x, which is k, and we just add or subtract those depending on what the problem is. If we're multiplying, simply just multiply the two limits together because that's the multiplication of two different functions. They're approaching the same value. Dividing, obviously k can equal 0, but you divide, same thing, just plug it in, there's substitution. And then finally, if you have a power f of x to a certain power, that limit's just going to be there. So, quick little examples, all right? Try these on your own. These are in your homework and whatnot, but when you have this, you take the limit as x approaches 4 for g of x equals 3. Okay, limit of x approaches 4 for f of x equals 0. So what would this be? Well, we have the limit as x approaches 4 g of x. We know that limit to equal 3. This is another function. As the limit as x approaches 4 for 3, well, what is that limit going to be? Well, that limit is that horizontal line. That's just going to be 3. Okay, so what is that going to be? Well, that's going to be 3 plus 3, which is 6. Awesome, huh? All right, so for this one, we're going to find the limit as x approaches 4 for x, and we're going to multiply that by the limit as x approaches 4 for f of x. Well, this limit right here, as x approaches 4, direct substitution is 4, times the limit as x approaches 4 for f of x, which we know is 0, so our limit's going to be 0. There we go. This one is a power property. We have this to second power, so this is actually the limit as x approaches 4 for g of x squared. That's how you write that. Well, limit as g of x squared is 3, so this just simply would be 3 squared, which is 9. It's 9. That's our limit. Moving on, what do we have here? Well, this one, we have a bunch of different ones. So if you take the limit as x approaches 4 for g of x over the limit as x approaches 4 for f of x minus, and essentially what we're doing is the limit as x approaches 4 for negative 1 or 1. All right, we just find each one of these limits separately. So what would that be? G of x we know is going to equal, we found that before, is 3. I'll write this in a different color. So this one equals 3 over, all right, limit as x approaches f of x we know is 0. You don't know, you can do that up on top. Yes, it equals 0. And then this limit, because it's a constant, it's a horizontal line, it's going to equal 1. So our answer is going to be negative 3. And those are the properties of limits. All right. Well, that is the homework. All right. And hopefully this will serve you well. All right. In solving these different various limits. There is one more lesson we're going to go through. All right. On trig and transcendental functions. But this was the majority of a lot of the problems that you need to do in going through and solving limits algebraically. So hopefully this helps you. All right. Answer some questions when we finally have class. But yeah, so good luck and God bless.